So we are Amphenol. We brought 6 of our RF business units to speak to you today about loss, noise, and distortion. As we get to each presenter's section, we'll go ahead and introduce the business unit and that speaker. So with any further ado, Chris Cooper, I'm the Director of Engineering at Times Microwave. I've been here for a little over a year, about a year and 6 months maybe. By study, I'm an electrical engineer. I got a master's in systems engineering. Consider myself an expert in RF and analog design, if that's possible. Done lots of systems with that incorporated phased array, wideband collection systems, phased arrays, beamforming networks, interferometry. Designed those boxes and then had to take them through full qual. So that's MIL standard 461. Even done aircraft integration testing, so MIL standard 464. So well versed in all of those aspects. Current projects, we're actually working on a multifunctional array aperture. We're designing synergizing across our business units. We're designing a TR module. We're packaging digitizers, VPX type solutions. We also have Amphenol military high speed that we're working on, network solutions, layer 3 ruggedized switches as a hardware platform. And then also we're working on distribution networks. So I'm going to do a systems focus, and then as we get to each one of our presenters afterwards, they'll focus on components in their area of expertise. So I'm going to do an RF systems general intro. We're going to look at challenges RF designers face, and then we'll talk a little bit briefly about Amphenol and the signal chain. We'll cover some systems figure of merits, and then we'll jump into a cascade before I hand it off. So. RF systems, I group them into 2 types: communication systems, non-communication systems. Communication system, everybody uses it every day. It's like a cell phone, for example. It's about information exchange. That information is typically a signal internal, right? It's modulated into the amplitude, phase, or frequency, and then we have to later demodulate that, decode it, decrypt it, what have you, to get that information back out. And then we have non-communication systems. So these are for like navigational aid. The best examples at the bottom of the slide. We have a commercial aircraft. There's at least a dozen systems that aid in navigation and positioning of the aircraft. Just to name a few: DME, distance measuring equipment; glide slope, that helps you ride the main beam to have a correct angle of depression down to the runway. TCAS, tactical collision avoidance system. Thank God for that one, right? ADS-B, which assists in air traffic control. The aircraft will actually, on a time interval at set frequencies, will advertise its velocity, position, etc. Obviously, there's work in directed energy, particle physics, and the main takeaway from this slide is that. If you look at the FCC and the frequency allocation charts, 95% of that spectrum is allocated. It's either licensed or it's set aside for military, scientific, or industrial use. And it's a crowded spectrum, right? So we have to design better systems to work in the presence of a crowded spectrum. So, this is something that's kind of breezed over in an RF 101 course. It's like on the first page of the first chapter. As an RF designer, the main challenge, or the main objective, I should say, is maximum signal power transfer. And there's a lot packed in that statement. It's kind of a deceiving statement. We don't want our system to contribute noise. We don't want to create distortion. And so, the textbook will get lost in a lot of fancy terms, like in order to achieve maximum signal power transfer, we have to have our source and load pins to be complex conjugates, which is a really fancy mathematical term for saying we want it to be mostly resistive and we want it to be matched. So typically we target 50 ohms for most applications. The main challenge designers face are what I call parasitics. So these show up in terms of like discontinuities whenever you're doing ground translation, or even when you implement components, like just taking the simple case of an inductor. To make an inductor, we need a conductor. The conductor has resistivity per unit length. It has inductance per unit length. When we coil that inductor up, we have two conductors separated by distance. So we introduce shunt capacitance. So we have to pay attention to self-resonant frequencies. That inductor is only an inductor for some subset of frequencies. It's not an inductor from DC to daylight like everybody would expect. So these are the challenges that we face, and how do we overcome those? We'll point this out as we go through the presentation, but it's paying attention to our material selection, paying attention to our processes, and that's inclusive of controlling our environments. So we want to continually evolve and figure out ways to reduce parasitics and achieve maximum power transfer. Switching gears a little bit, again, I'm more of a system focus on my portion of the presentation. This is what I would call a generic system. It doesn't matter if it's a cell phone. It doesn't matter if it's a mission system on a military aircraft. Any RF system, it's going to have these basic elements. That's an antenna or an antenna array. Its main job is to resonate, is to intercept the signal. We're going to have some chain of analog signal processing. The attempt is to move the digital signal processing further and further up that chain. But we're never going to get rid of the need for analog signal processing. This includes balun, low noise amplifiers, switch matrices, et cetera, right? Then we have digital signal processing. Should have started my timer. And then we go into network and compute solutions. And then ultimately those data products are going to be on some type of human-machine interface for the individuals using that system. So this is your generalized RF system block diagram. Historically, when you heard Amphenol, you thought your trusted interconnects design partner. So we've worked, just throwing a few examples out real quick. Times Microwave has been your Group A cable experts. We've innovated products such as Miltech since the 1970s. We've been on pretty much every military platform you can imagine. We're also the innovators of LMR since the early 90s that offset all of your, the only other options you had at the time was RG cable types. And then also we innovated more recently, about 20 years ago, phase track, and we're still innovating new things with Levitate and other products that we've showcased at the booth. Inside the LRUs, a good example of SV microwave or Amphenol CDI doing board to wire, RF board launches, and then Amphenol APC. Board is really an interconnect between semiconductor processes, and then also SV is definitely a brand name, dominant brand name in all of your open system architecture standards such as SOSA. And then Amphenol has all your solutions, whether it be copper or fiber-based. And so this is where, when people think Amphenol, this is what they see. With these 6 business units that we're showcasing, we've really attacked the signal chain. We've gone deeper into the signal chain. And so now we have component offerings across the analog signal processing to include digital signal processing through IRF. So, and then ultimately, or at the end of the signal chain, we also have rugged layer 3 type switch solutions as well. We can move at 100 gig E, basically your latest serial speeds. All right, stepping forward. I'm not going to hit on each of these individually. Like I say, as the speaker comes up, we'll dig a little deeper to introduce you to each one of these business units and the speaker themselves. But here they are if you want to see them on one slide. I'm going to jump into figures of merits, just kind of covering some basics. Being an RF engineer, we work from anything from 1 nanowatt to 1 gigawatt, a lot of zeros. So we like to compress that down into logarithmic scales. Also, there's the advantage of logarithmic properties where multiplication in linear is really addition in log, and then also division is subtraction, so it makes it very easy to move around. I've gotten pretty comfortable, whether it be terms of relative, which is dB, or terms of absolute, which is relative to 1 milliwatt. So that's the differentiator between dB and dBm. I've kind of committed to memory. 30 dBm is 1 watt. If I go 10 dB from that, 30 dBm to 40 dBm is 10 watts. If I go 10 dB less, 30 dBm to 20 dBm, that's 0.1 or 100 milliwatts. Again, you'll learn other shortcuts. 3 dB is 2 times, minus 3 dB is half. 4 times is 6 dB, 1 dB is about 20%. So I can very quickly interchange linear to log. So it's an acquired taste, but I'd encourage you to get very comfortable with decibels, because even on this next slide, I'm gonna interchange noise factor and noise figure pretty quickly. But so tying back, everything we're doing is about maximum signal power transfer. So those are all going to be specified in terms of decibels. Noise figure, again, this is what our contribution to the level of noise from our system. The first definition to cover is thermal noise floor. That's KTB. It's a constant times the temperature times the bandwidth. Here on Earth, we kind of use 25 degrees C as kind of your ambient temperature. We use a 1 hertz bandwidth, and then it's an absolute measurement, so it's relative to 1 milliwatt. So the thermal noise floor is about 174 dBm per hertz. If I had a signal in the ambient environment and I had a system with gain, that signal would go up by the gain of the system. However, the noise floor goes up by gain plus noise figure. So this is the contribution of noise that your system adds. So that's why it's a very important figure of merit. It degrades your signal to noise ratio. And so we do our best to minimize this. So one of the tricks to minimize this is looking closely at the equation. Your first stage adds 1 for 1 to your noise figure. So the formula is in noise factor. That first stage is dominant. Thereafter, every stage is reduced by the gain of the first device. It's how typically the first device. So I've got its name, the low noise amplifier. So I do kind of a real quick sniff test to know if I'm gain starved on a system. Is I look at the noise figure of the stages after the low noise amplifier. I try to size my amplifier. So for example, if my digitizer or spectrum analyzer or whatever I'm driving has, say, a 20-25 dB noise figure, I try to get 25 to 30 dB of gain to minimize their effects of noise contribution. So that would be one example of how to use that equation to your favor. As I step forward, you're going to learn, though, a lot of people throw a lot of gain up front and don't think of the effects, because if 25 dB gain is good, then 35 is better, right? And that is not the case. Gain distribution and gain balance is actually a very important thing to weigh and consider. And that affects what we call compression and linearity. So what you find is with this formula is that gain in the back stages drive your compression point and drive your linearity. So just quick definitions to cover our bases here. So the P1 dB is the point if I have a graph where I have P in versus P out displayed and I increase my power input, the output should step 1 for 1. It will into a point of, you run out of DC headroom. That point, the gain will suffer a 1 dB drop. That is your 1 dB compression point. As you continue to step power up, you'll see that the power out asymptotes. And so that's saturated power. It usually occurs for like gas parts about 3 to 5 dB into compression. For GaN devices, that's not always the case. They go into soft compression. They kind of have a second gear. They throw it in second gear, and I've measured parts that have gone 12, 15 dB before they fully saturated. The other figure of merit is quantifying how much distortion we add to a circuit. We typically use a two-tone test method, and it's called intermodulation distortion. When we introduce two tones to a nonlinear device, such as an amplifier, they intermodulate and create distortion products. So we have third order and second order are pretty classic measurements that we make. Third order being you take two tones, F1, F2, and what you get is the 2 times F1 minus F2 and 2 times F2 minus F1, and they put two sidebands, which we call IP3, and these are usually the most critical parameter because they fall in band. For example, if I place those two tones 1 megahertz apart, the distortion tones are only 1 megahertz from my carrier. So they can't be filtered out. If you're looking at a receiver, this is probably one of the main parameters you're looking at, along with instantaneous bandwidth. So we call it IMD3. We project the line of where it actually crosses your P in versus P out. It's a fictitious point. And we calculate it by the delta of the power of the carriers to the relative power of the tone. And we calculate that point. That point is purely such that I can compare two amplifiers, two components, two receivers to each other and know which is better. The higher number is a more linear device, okay? So we talked about noise figure in the prior slide. That has to deal with how sensitive my system is. If we talk with distortion, this is how well my system reacts to very large signals or numerous signals. So again, what I'm trying to do is define a baseline for noise sensitivity, noise affecting sensitivity, and multiple tones and large signals affecting distortion of your system. So again, when you do a cascade analysis, it's all about gain distribution, applying the right gain at the right stage to achieve optimal dynamic range. Okay, we're actually going to look at a little cascade example here. We're going to start with a pretty generic block diagram, just a software-defined radio. We have an antenna. We have what I call an antenna feeder, coaxial cable from our antenna to our front end. Again, it's a very critical stage, especially if you're doing interferometry or beam forming. You need something that is very amplitude and phase stable, low loss. And then we're going to launch into that board through some connectors. So we'll look at some connector launches and approaches for that. We're going to step through a low pass filter and cut out some of the ambient noise. And then we're going to go through an LNA into an equalizer or attenuator, which we'll look at some thin film techniques. And then we're going to launch back out the front end, go to a coax, and go to a 3U VPX digitizer. Everybody has, anybody that's an RF engineer has taken those equations and thrown them into an Excel spreadsheet. Every engineer I met has their own version. This one is mine, ugly or pretty, whichever have you. What I want to point out is I took 3 columns and I cut basically the same block diagram in 3 instances, and I added variability of the first stage. And so I've been challenged to use this pointer, so I'll go ahead and hopefully you can still hear my voice, but I'll make do on, oh yeah. That's why we have Phil. Okay, so I've added variance to the first stage. It's about 0.6 of a dB. Again, for a passive device, your loss is actually the same thing as your noise figure contribution. It's very quick, intuitive to me, because if my signal power drops by 1 dB, it's the same as the noise floor coming up 1 dB. So I've modeled that coaxial feeder antenna coaxial feeder. And again, you can see the difference of buying a high quality cable with very low loss, under 0.5 dB, versus buying a cheaper cable that has over 1 dB of loss. It's a 1-for-1 hit. So again, like I've added the variation of 0.6 of a dB, you see exactly, actually, I think I have another number altered. Yeah, I have the last stage. Yeah, let me back that up. So I have both the coaxial feeder variance and the digitizer feeder. I have cable variance. So you see the first stage is giving a 1-for-1, and then we're getting a few tenths of a dB from the last stage as well. So that's telling you I'm a little bit gain starved. I don't have enough LNA, so I probably need to go size my LNA just a little bit bigger. So that's the first step, is kind of reinforcing that noise figure equation that first device is critical. Next, we're going to look at, just kind of highlight that output cable loss. We're going to look at our linearity and our compression point. Because it's not the final stage, because I have the digitizer setting the compression and the linearity, it's not as impactful, but you can see that loss contribution actually affects those calculations. And then finally, I'm going to add variance across the cascade. And in some aspects, I'm adding 0.5 dB. In aspects of the microchip transmission line, I'm adding very small 0.08 dB. But the takeaway here is that these small contributions add up. And if you look at the overall predicted system noise figure, I have an 8 dB on the best case, the most optimal case. On the worst case, I've actually accrued 6 dB of noise figure. If you're making a link, 6 dB noise figure actually just decreased your transmission, your reception distance by half. So that's pretty critical if you're trying to make the better radar and not be shot down. Likewise, you can see the hits on IP2, IP3, and compression point. Again, because the digitizer is the last stage, it dominates this cascade, and that's kind of what you want. But that's the key takeaways. I'm going to hand it over to Phil, who's going to walk you through some coaxial. Thank you.
Thanks, Chris. Great information. So hello, my name is Phil Lenk. For those who don't know me, I'm currently a product manager at Micro-Coax. Been there since 2011 in various positions, both in inside operations, inside engineering, external engineering, and sales field work. And I'm going to walk you through a little bit of our coaxial cable portion that we at Micro-Coax focus on there. And through these talks, I'm going to try to make a little reference and analogies to the music world, because if you take a step back, audio and music is RF that we can hear, and how can we use that to simulate and understand microwaves that we can't see and we can hear. So let's start unpacking this, and starting with really the coaxial cable in its basis. So thinking of things that were innovated, at Micro-Coax, we take pride in innovating the semi-rigid coaxial cable. Nearly 100 years ago, our founder owned the patent to metal shielded wire. And that's what's shown on the left here is a very simple RF cable, center conductor, dielectric outer conductor. That's great. It has fantastic properties. It's very smooth conductor. It's great at transmitting energy down it, but it's rigid. It's stiff, and there still has many applications today. But it's been around the block a few times, and we're looking to say, how can we take that to the next level? How do we take that simple RF cable and make it where I can flex it and put it into whatever the heck I wanted to put it into? And that's the second picture here. We take that outer conductor, which is a rigid copper tube or aluminum or a different material, and add more flexible type metal layers that can now move around a little bit. And now we have a flexible cable. That's wonderful. And then how do we take it a step further? That's the picture on the right, which is that same basic cable on the first few layers. And then the bottom half of that shows these more ruggedization and armor type layers, be that internal or external armoring. And through that, we're seeing how can we minimize the loss that's introduced into the cable? How do we reduce the reflections that are happening inside of the cable? And I'll go through a couple examples with that, but there's a lot of know-how and design that go into making a cable that can do those things and transmit your signal properly through it. And not just the cable, but on the far right, we have the connectors. Connectors also have to be designed and maintained and installed in manners that will minimize mismatches, impedance mismatches, or reflection that viswire gets introduced into the system. So here is a simple case study looking at two typical cables in the industry and looking how they perform over an S21 or an insertion loss plot. So taking the step back to audio world, things that we can hear, imagine you're playing guitar and you have a nice long run from here to the back of the room where my amplifier is at, but I chose a really poor quality cable that introduced distortion and noise. When I'm playing guitar, I love distortion, but when I'm trying to give an RF signal, I don't like distortion. So I need to pick a cable that's of high quality that can really transmit that signal properly. So here, looking at the black line, we have a industry standard 190 cable. That's 190 thousandths diameter at the OD. That's rated up to 26.5 gigahertz, very common. And at Micro-Coax, we took a kind of different philosophy where we started with a conductor that was inherently larger in order to give us a better insertion loss signal across the length of that cable, while still maintaining that 26.5 gigahertz line size, which then pushed the diameter a little bit bigger, but we have ways of mitigating some of those different properties there. So within that, we're able to maintain geometry and signal integrity to minimize signal loss within your system. And as Chris was going through those examples of our fictitious system, we need to have ways to mitigate loss and noise and distortion throughout it there. So speaking of loss, noise, and distortion, let's talk about noise for a couple of things here. So noise, which we heard a few times come into this room now, is unwanted signals that are getting into our transmission path. And within a cable assembly, one of those points that we showed in our system, there were a number of cases which can lead to that. So back to the audio analogy, imagine who's a popular singer to these days? Taylor Swift. She's recording a new acoustic track, just her and a guitar in a sound booth, and it's going to be very lovely, nice and rich sound coming through. But for some reason, in the recording studio next door to her is Slipknot or Dream Theater. Somebody's playing very, very heavy music, but the walls were not engineered properly to mitigate that sound propagation into her. So now she's getting all this external sound into her sound booth, and we're getting this noise, unwanted noise, and it's a similar concept within our cables. Like that audio engineer should have designed a better wall or a better insulation in that wall, but they didn't for some reason. We take that same philosophy, not audio, but of RF microwave energy within our cables, cable designs, and connectors. So thinking of RF ingress, some of those things that we need to care about is crosstalks. In the picture on the right, we have a high density parallel runs of cable where signals, if they're not properly shielded, could go from one to the other, or even external influences coming into that outside of there. Within the connector design, how are those internal designs maintained for the connections to happen? How are the joints? Are they attached to the cable with a crimp or with a solder? At Micro-Coax, we exclusively use solder connections to give a nice full solder around the back of the connector to the cable. Again, to have a nice solid thing with no voids. If you have some crimps, sometimes there could be pinholes in allowing energy to come in or energy to go out. All things to consider there within the cable itself and cable shielding. How is that used to mitigate unwanted noise? So let's look at two case studies. On the left, the very first picture you'll see is a typical two-shielded coaxial cable, not unlike the ones we saw earlier that can be rated up to 26.5 gigahertz, very common. And on the bottom left graph, you see a dotted dashed line. That was tested and measured at our factory where we have a stirred mode reverberation chamber to test RF shielding properties. And that cable performed out to 18 gigahertz, roughly around 65 dB of loss through the cable. And one of the things that we developed at Micro-Coax is a product called Aerocon. And if you look at my socks today, I'm actually wearing Aerocon socks. And to lighten it up a little bit, if each of you just takes one moment and reaches underneath your seats, yeah, you'll find there's nothing there. But in the back, we do have socks for you to pick up on your way out if you haven't get one. But Aerocon it's not actually a cotton, it's a Kevlar-based fiber, a textile that we then metallized and plate in-house at Micro-Coax. And in this example, we took this shield, put it over top of that same wire, tested it in the same manner, in the same chamber, and that gave a 30 dB of improvement in shielding. So basically riding the noise filler of our chambers. So this is a fantastic material, which is, if you can kind of think of an analogy of a chainmail suit, which you would wear in typical combat and armoring, it has a lot of holes, but you can still move it around versus my t-shirt here, which is very dense fibers, and that's more like our Aerocon, so it's fantastic at rejecting high frequency energy into our cables. And the other picture on the right is for an industry standard SMP, typically out to 18 gigahertz, which we measured on the bottom right graph there. We see typical shielding, that's either noise coming in and noise going out through that push-on interface at 65 dB. Now at Micro-Coax, we developed a new technique on our female connectors that was able to push that up another 15 dB, which pushes a standard SMP interface up to 80 dB, which is pretty industry changing, and we're very proud of that recent design. Still completely intermatable with other third-party connectors or our own male connectors. I'm happy to talk more about that. So lastly, we're going to end with sources of distortion within our cable. Again, we heard distortion today multiple times. And back to the audio analogy, if I'm playing guitar, I want to have distortion in my signal typically if I'm playing something heavier or reverb or chorus. But if I'm making VNA test leads, the last thing I want to have is that distortion introduced into the cable, especially after a fresh calibration and going to do a whole day of testing. This past year, we had a lot of hard work go into our latest AccuPhase test cables, which are meant to be calibrated once in the beginning of the day, be flexed, moved, banged around, moved, tested all day long, and still hold that initial change, especially in regards to phase versus flexing, particularly in these models here, where they're meant to mitigate any of those distortion introduced through bending, movement, vibrations. And it didn't come overnight. It came over those decades of experience that we built into our Utaflex products and know-how within the industry of the metals and various techniques of cable and cable building. So with that, I wrap it up here and say that when we're looking at a system, it's not just one part, but the whole system must be evaluated and work together to provide an ultimate wave to go through. So with that, I stop and I hand it over to Evan. Good luck.
Hi, I'm Evan Tarr, Principal Electrical Engineer with SV Microwave. I've been with the company for a little over 20 years now, starting as an intern just before we joined the Amphenol family. We primarily work with passive coaxial cables connectors, anywhere from a few megahertz up to over 100 gigahertz, and mostly supporting defense industry, space, test and measurement, really anyone that'll have us. And today I'm here to talk to you about getting from the cable to the PCB. So Phil might make a perfect cable, and Colby, APC, may make a optimized PCB, but getting between the two is where a lot of problems can show up. There are many different types of cables, different sizes, many different types of PCBs, and there's no one solution that can perfectly solve all combinations there. Any general design errors can cause huge broadband issues in your return loss, insertion loss, and small mistakes or errors may drive a deep resonance or suck out and totally kill your performance. So these very complex systems pushing to higher frequencies all the time, we're very lucky to now have very elaborate full wave 3D EMAG simulation tools such as CST and HFSS. These greatly simplify getting complex designs to high performance. One huge benefit in the last 5 or 6 years is the introduction of encrypted models. So these allow us to take our full 3D models of our connectors, put them up on our website in encrypted form so that they can be loaded into a customer's project. They'll get the full EM performance when they're running their simulations while still obscuring our proprietary geometry and design inside of it. These are great for helping the customer use our connectors and integrate them into their designs. But if they don't have these tools or the know-how of how to use them well, we also, of course, do offer to do that design for them. They submit all their PCB information, what they're trying to do with it, what their frequency is, and we'll spit out a full formed footprint for them. That footprint refers to just basically the geometry and layout requirements for the PCB in order to accept our connector. It's important to remember always with simulation though, that everything is looking as good as it's ever going to look for you. In the real world, once you install these things, you're dealing with tolerances, inconsistencies, solder, people doing assembly. Everything's going to look a little worse, so we always shoot for the absolute best we can at this stage. So, as I said, there are a lot of different ways to get from the cable to the board. This could involve solder, very often, of course. And with solder comes a lot of inconsistencies. The very high temps involved can cause a great deal of problems during reflow, especially if the individual components are not meant to hit that high of a temperature for that long of a time. And if you try to go for hand soldering, you're likely going to end up with a very messy board and possibly shorts or other issues in performance. So one of the easiest ways to avoid solder is to go with a solderless connector. We have solderless compression mount connectors, as we call them, that use an interference fit, purely mechanical, working with hardware with the board. So that just means that the center conductor is going to sit a bit proud of the body of the connector and will be gently pushed into the core and copper on the surface of the board. Just takes a few screws and a steady hand and you can easily install them. And those can give us great performance, but they of course come with some downsides. You don't get the permanence of having the solder on there. They may not operate well during very high shock or vibe environments. So the angle you approach the board. Coming in from the edge, an edge launch connector tends to give you the best performance. The transmission lines are on axis with each other, which greatly helps. Unfortunately, there is limited real estate on a board. There's only so much edge. So edge launches, there's limited real estate. There's only so much edge on the board. It might not be near the next component you're trying to get to. Surface mount can be great because you can place the connector right next to your next component. A lot of options there. But the right angle format of getting onto the board can greatly reduce your max frequency and add a lot of reflections and general trouble with your signal. We do offer a 30-degree connector, which is sort of the best of both worlds. It sits on the surface of the board, but comes in at a 30-degree angle. It's kind of close enough to get essentially the performance of the edge launch, but the versatility of the surface mount connectors does come at added complexity, which means cost and the physical footprint of it. But you can really get excellent performance just about anywhere with it. So getting to the edge of the board sounds easier than it is, because if you don't get directly flush to the edge, you're going to be left with an air gap. That air gap is going to cause generally large suckouts and huge reflections. Might be narrowband, depends on the size of the gap really. So it may look like you're holding nice and flush on the board, but the second you put that in the reflow oven, things can shift and cause a lot of problems there. You may need custom fixturing, or that could be disposable or built into it. We do offer a product called Edge Lock. You can see in the bottom right here. These have, if we give precision drilled holes on the edge of the board, this connector has tapered legs on the end of it, so that as you install it, it'll pull up real nice, snug, and flush against the edge of the board and snap right in, hold in place through the full refill process, so you don't have to worry about that. And even if you manage to keep it exactly flush, many fabs have requirements of copper pullback. And that is to say that the copper, they will not want to run it all the way to the very edge of the board due to when they go through the milling process, it can tear, cause various problems. So this is a reality we have to deal with sometimes, and it's pretty much just as bad as having that air gap. It's going to cause a lot of problems with your signal integrity. A cleverly designed connector, such as our Edge Plus line and some others out there, will have the top half of the body extend out over the board so that that ground plane can make immediate contact with the ground plane of the board and bridge that gap. A lot of times the issue is not directly with the connector mounting to the board, it's issues that come with working board-to-board connections with an E dangling off the end. Yeah, if your backplane and daughter card are lined up perfectly, that sounds wonderful. It's never going to happen though. So you'll be dealing with air gaps once again that come down to offsets. And those offsets could be radial. If the center lines of the two boards are offset slightly, that's going to have your connector tilted slightly, and that's of course going to cause problems, noise, distortion, or axial. Maintaining a tight tolerance of the board-to-board distance is a difficult thing to handle in more complex systems. And that is going to cause an air gap at the interface of the connector on at least one side. So most common and cheapest way to bring the two together is what we call a fixed length bullet. These again, cheap and easy to use, but they have no control over the gaps that are going to come with them. You can use a compressible spring bullet, and that will have a range of compression it'll operate over. That will fill up all the axial gaps and soak up a little bit of the radial gap while maintaining a full 50 ohm line through the length of the connector. So it'll keep your performance nice and low, but it does come, of course, with added cost and complexity. The SMPM XT is a new line. This is essentially for lower frequency, generally applications, but this has an extended pin and socket. So you might have a large air gap remaining, but it still will maintain contact may not want to use it above 5 or 10 gigahertz, but sometimes having a mediocre performance is far superior to having just an open circuit. So there's sacrifices to be made at all times here. And of course, as frequencies push higher and power levels push higher, everything is getting denser within a small box. You don't have to worry about just your individual connection, but what's leaking out of it. Like the shielding Phil was just talking about, this is a concern as well. You have a beautifully shielded cable and a perfectly designed strip line with lots of ground vias to hold everything EMI tight in there. Still getting between the two is where you'll run into many problems. There are different transmission line types you could be launching to. If you're going to a surface trace such as a CPW or microstrip, these are inherently going to be a bit leaky amongst each other. But the current approach is typically to use gaskets or bespoke shielding. This can be expensive and complex to install. We do some connectors will handle that for you. We have shielded edge launch connectors, you can see in the center of the screen there, that will completely cover the entire RF chain from through the connector and completely shielded onto the board with an EMI gasket on the lid on there. So the lid's removable. You can still inspect your solder joint, which is a frequent concern, but that'll keep it extremely EMI tight. Of course, the connector is only as good as the board it's attaching to as well. So there are many other techniques that can be done on the PCB to help improve this a great deal as well, such as edge plating. If you have a multi-port connector and the whole thing, say there's copper pullback on interior layers, or you get one of those terrible air gaps at the edge, all of those ports are going to be bleeding into each other and into the rest of the box or all the other components out there. The edge plating will give it a nice surface to fully shield that and attach well to the connector on the edge of the board instead of just the surface. But if we are going to get into PCB technologies, I have someone far more capable to discuss that. So, Colby? We take the risk aside.
Hi everyone, my name is Colby Hobart. I'm the RF applications engineer at Amphenol Printed Circuits. We are headquartered in Nashua, New Hampshire. At Amphenol Printed Circuits, we do all high complexity circuit board work and circuit board assembly. Our three main product lines would be RF, HDI, high speed, and flex and rigid flex. And it is almost entirely defense work at this point. My background is I was a RF circuit design engineer, passive radar front end type stuff, beamforming networks and antennas for about 10 years. And then I've been in circuit board shops as a passive RF SME for the last 12. Today I want to talk about, referencing what Chris was saying, how, the goal of these RF systems is maximum signal power transfer and how we can contribute to that in the circuit board fab. So when we're not etching distributed element components onto our copper layers like antennas and couplers and power dividers, our only job is to connect signal from point A to point B with minimal insertion loss to achieve that maximum signal power transfer. And so there's a few ways we can do that. There's kind of 4 components to insertion loss. A lot of you are familiar with this. So you've got ohmic loss in your conductor, which relates a lot to roughness, since basically all we use as conductors at the board shop are copper. Our ohmic loss usually is based on how rough that copper is. There's also dielectric loss in the dielectric materials separating the copper layers. You can have radiative loss, which we won't really touch on today. That's kind of limited to microstrip because in a well-designed strip line, you shouldn't have much of any radiative loss. And then return loss. So your reflections, any of your reflections in your system are going to show up at the far end in your insertion loss. That signal doesn't make it to the other side. So on that ohmic loss front, we make all of our circuits out of copper-clad laminates. And we go in, we image and etch different layers. And from there, we put prepreg or adhesives between the dielectric cores, copper-clad dielectric cores, and laminate them together. but we need to make sure that they're going to stick. And so we need to roughen up that copper to some amount, but that's always going to be a trade-off with insertion loss or signal loss. And so outside of RF, we would just run a standard, what we call bond, which is an alpha prep chemistry that micro-etches the surface of the copper to give it a higher roughness so that it'll stick during lamination. But when we get into RF, we start having to try to balance that to not have too much signal loss. So we run also a reduced recipe bond, and we also have a process where on layers where we have copper fill and signals, we can keep the bond entirely off the signal trace. Only the commercial market has really allowed us to ship products like that so far, but as demands get higher for lower loss, we may see that coming into the defense market as well. And so this chart just kind of illustrates, looking at laser profilometry of standard bond, reduced bond, and no bond on the signal traces. And then we talk about insertion loss in a couple of different scenarios with full bond, reduced, and no bond. And you can see that the no bond case really, really drives down the insertion loss. That's super ideal. But when we can't use that, we can migrate up to the red trace and still save a lot of insertion loss by being mindful of that balancing act between adhesion and low loss. Then on the dielectric loss front, so that's the loss between your signal layer referencing your ground planes and strip line one above and below, or microstrip one below, and then coplanar, Evan was talking about as a different situation on layer grounding. But the electric field lines have to pass through dielectric, and the more loss that dielectric contains, or the higher the dielectric loss tangent, the more power you're going to dissipate in your dielectric. And so we want to use the lowest loss dielectrics. We don't want the dielectric to have more than maybe a 25% contribution to our total loss because ohmic losses are so high, we have to control the dielectric so that we can keep the total loss manageable. Teflon has always been kind of the gold standard of low loss dielectrics. We do process Teflon in Nashua. We have several products on the floor using Teflon. It's very difficult to process, very difficult to drill, to not drag that soft material over an interlayer pad interconnect. So when you plate to the pad, you have a DC connection. And then if you do drag some over, you can't do anything to kind of etch it back or burn it back like you can on traditional laminates. So the good news is, although you could tell from this chart, nothing has really beaten Teflon in the dissipation factor. All these materials used to be much higher to the right, off the chart, and are slowly migrating in toward and approaching Teflon. And it's a combination of the dielectric material and the smoother foils that people are using stock to get us there. So right now in engineering, we've got 4 new very low loss materials that are from that resin-based system camp. Much easier to process and almost as low loss as Teflon. So we've got Panasonic's Megtron 8. We got 2 materials from EMC, the 892K and the 896K2, and also from Isola Tachyon 200J is their latest lowest loss material. So we're qualifying all of those. If you look on the spec sheets, you'll notice like when they calculate the dissipation factor for these materials, they're using a variety of different test methods from IEEE. And you kind of get the feeling these manufacturers are kind of picking the one that they got the best result with. And so we reference those, and those are what gets our attention. But in the end, we're going to go make strip lines out of all of these. And with a long and a short strip line, we are able to calculate loss per inch, apples to apples across the different materials. So we can work with our customers directly and say, despite this chart, this material is actually equal to this as far as loss per inch on a typical strip line with the copper that they have, these 1.5 micron roughness coppers that we're using these days. Now, as far as reflection, the reflection component, viswar, return loss, when your signal's traveling down a transmission line and it hits an unexpected impedance or a different impedance for some length, some appreciable length, maybe 40th of a wavelength on the conservative end, or a 20th of the wavelength, or a 10th. People use different numbers of the impact of when return loss starts to matter for insertion loss, but it's some fraction of a wavelength that you've got an off impedance, and sometimes you can't help it, or sometimes it's a mistake. But the reflection that's generated, traveling from your probably 50 ohm single-ended line or 100 ohm differential line into this off impedance doesn't get to your other side. So you're missing out on some of that maximum signal power transfer. And it can be hard in a circuit board because we're going along in a TEM or quasi-TEM mode, microstrip or strip line, and then we have to transition layers so that we can route and fit all our plumbing in. And so we've got to go down into a coaxial mode now, which is going to be a plated through hole on the signal, the two signal pads surrounded by plated through holes connecting all the grounds. And that looks like a coax cable going down through the board. And then you take another turn to another strip line and you're going this way again. So your field lines, on your microstrip are down out of the microstrip. And then you transition to coax, all of a sudden your field lines are going this way. And then down to strip line, you've got field lines going this way all of a sudden. So there's always going to be some reflections in these, and you'll see features on the traces that our customers design to kind of match that out or tune that out. But it's a static tuning. It's a feature they put in there that's going to give you the best return loss down through the via onto your transition, like a little short high impedance section or low impedance section or a combination. So one big way that we can actually help to control this return loss is by stub control. So in the top left here, if you're looking at the through hole on the left side, that may be connecting layer 1 to layer 2, a microstrip on layer 1 to a strip line on layer 2, and then layers 3, 4, 5, and 6 are all this kind of extra plated through hole. And depending on your frequency, as you come down and you transition to layer 2, that might look like a T-junction. Some of your power might go down, and there might be some bandwidth-dependent reflection, and some other will rejoin, maybe in phase your circuit on layer 2. But you're definitely getting some unwanted reflections there and losing out on your signal power transfer. So there's different ways we control that stub, and that's what this slide is really about, is controlling that extra via that we don't want, but it's part of processing. So one way is back drilling in the bottom left. So we can, on the right side of that, we can drill that through hole and then plate it. And then we can take a larger diameter for registration, larger diameter drill on the drill machine, and drill down and remove some of that stub. And then we fill that with hole fill, and we can plate over it to reconnect that ground so you don't have any radiative loss or crosstalk out of there. We can also do sub constructions, right? So we can build 2 3-layer boards essentially, right, and drill them and plate them, even doing some back drilling there, and then bring them together at a composite. So we don't have all the extra stub layers 4 through 6 if we're just concerned with layers 1 through 3 on that first drill. It makes processing more complex. We're building 2 boards and then another board out of the 2 boards, but it's really effective for stub control. We can also do, similar to how microvias are made. Microvia is a stubless connection through these very thin layers of adhesive and a foil layer. But we can do larger diameter, deeper vias that have no stub using that concept. So we can start by a mechanical peck to get close to the target layer, and then laser to the target layer in the top right here, and then plate that blind hole. Now, the limitations on plating a blind hole are a lot stricter than a through hole, but that allows us a 0 stub option. And that's going to be very important, as we start seeing more migration above like Ka band, into W bands and Q bands and things like that. We are seeing the military doing research on that sort of thing now. So I think it's a matter of time before we're having to build to that frequency. And then controlled depth drilling is kind of like a deep laser via. It's much faster and easier. So if you can deal with a little bit of a stub, then you can drill just past the target layer. And as long as that's a 1-to-1 ratio, we can still plate that and make that connection. Comparing to like a through hole, we can do like a 10-to-1 or probably even 20-to-1 aspect ratio depending on the parameters there. So there are limitations to these blind holes like a deep laser via or controlled depth drilling, but it can be a very easy way to get 0 stub at the same time. And that's it for my portion on circuit boards. I'd like to introduce David Higginson next from Q Microwave. He's going to talk about subsystems, bringing all this stuff together into a subsystem designed by Amphenol.
Good afternoon, everyone. As Colby introduced me, I'm David Higginson. I'm the Director of Sales for Q Microwave. We've been part of Amphenol now for a little over 2 years, so we're a little newer to the group. I am going to cover RF filters. And RF filters are really going to help you focus and narrow in on the signals that you want to listen to or communicate across. Many of my colleagues have talked about the RF spectrum being very noisy. We have a lot of things in the air. And so you want to narrow down what you want to actually focus on in your RF spectrum. RF filters are what help you do that. So we have our basic high-pass filter. It's going to pass everything that is higher frequency, and you're going to reject all your low-frequency signals. You have your low-pass filter, which is going to pass low frequencies and reject your high-frequency signals. And then most often used is your bandpass filter, because you want to narrow in on one section or one region of your frequency spectrum. And then we also have seen band stop, reject, or notch filters. Maybe you just want to get rid of some ugly harmonic or some terrible signal in the air that is causing distortion to your system. So you just want to get rid of that because everything else is working fine. So we can do a notch filter and just get rid of that signal. So I'm going to touch on some theoretical Q, which is actually where Q Microwave gets its name. The Q factor is something that's not really talked about much anymore, but is still very, very important in terms of microwave filters. The Q factor is essentially a unitless measurement that the theoretical limit, if it was infinity, would give you the perfect theoretical filter, a perfect square of what you want, only isolating the signal you want to listen to. But that's all theoretical. So realistically, Q is somewhat relationship to the size of material and the types of material that it is. So a lumped element filter, which is just your basic single layer caps and air wound coils, typically have an unloaded Q somewhere between 50 to 150. Your ceramics resonators, those are going to have a slightly higher Q, but again, they're slightly larger in size. And they're going to have somewhere between 300 to 600. And your comb line or cavity filters, which are much larger in size, are going to have a much larger Q factor in the 2,000 to 5,000 range. So a lot of times we have engineers come and ask us, and they want a perfect filter, and they want it as small as possible, and want to reject their signals. But there's a lot of trade-offs that have to be made within RF filters. So we take a look at how that trade-off is going to function within the number of sections of an RF filter, how that looks like for your rejections, what are you really trying to get rid of? Because the more sections, which equals the more rejection I get, the higher the insertion loss. So as Chris was talking about before, I'm going to impact my noise figure with more insertion loss now. Because this is a purely passive device, I'm purely going to get that impact to noise figure. And although it may be after a LNA or anything other gain devices, you're still getting that impact. So you want to limit the amount of insertion loss that you're getting off of that. Now, as we have that filter, we can change the number of sections based on what the customer need is, because we want to understand truly, we want to get right on that perfect edge of what you need while limiting the amount of insertion loss that you're seeing. So bringing that together with the Q factor, you can see here that in a 7th order Chebyshev filter, which is a fairly common filter, depending on the type of topology or the type of filter we do, you can have a lumped element ceramic or comb line that do the exact same thing, exact same filter, exact same bandwidths, but because of the level of Q or the unloaded Q that each of them have, the actual filter shape is going to vary. So with a lumped element, I can make this much smaller. I can be about 3/4 of an inch long by 3/100 wide and 3/100 in height. But you can see that the performance trade-off is I'm going to get somewhere in the -2 dB of insertion loss. Well, then we have a customer saying, hey, I can't tolerate that. I need better insertion loss. Okay, well, we can go to a ceramic filter, but you're going to get larger. You're going to have larger characteristics of that. So now you're about 1.25 inches long, a little bit bigger on the width and a little bit, probably about the same on the height. And you get much better performance. And then they could say, oh, I still need better insertion loss. I can't tolerate that. Well, we can move you to a comb line or a cavity filter. Well, now you're going to be about 4.5 inches long. Or there's different tricks that Q Microwave has learned over the years to try to mitigate that. But overall, physics is physics, and we can only change things as much as it's going to allow us. So you will get larger in size. Now, we talked about on the actual boards, how are we connecting everything together? We have Amphenol printed circuits and SV, we're getting to the board. How do you connect to these filters? And so some of that can determine how much insertion loss, what that package looks like, and these become very critical factors, like Colby was mentioning, is how you're launching in and out of something. If you have vias or stubs, you have a lot of mismatches, which will cause VISWAR issues and increase your return loss and worsen your return loss and worsen your insertion loss. So we work very closely with our customers to look at what best meets your need for the exact frequency range you're looking at. Because we can do something of a formed lead, like you see there in the middle, where you can go from DC to 4 gigahertz. It's very useful to do that on the board, reflow it on. You're gonna get good isolation on that. But maybe you need something that goes a little bit wider in frequency. So we're working up higher, and we can move to a castellated via approach where it's a lot harder to do, and maybe we have to match the board materials, but it's going to work at a much higher frequency. And then you could go to a more of a blind via approach where you're not going to be able to see the solder joint or the location where it's actually connected, but you're going to be able to really reduce any radiation that may be coming off of that transition. And you're going to be able to look at a much higher frequency range, getting up into the 20 gigahertz range. And then microstrip launches is traditionally what we see across the industry. You're having a microstrip or a ground signal ground. This is what a lot of different RF components use. Now, RF filters are very unique in the industry, where we may have to generate that package depending on that exact frequency band that you're looking at. We want to optimize it as best we can for the frequency range that you're working across. So this is a quick reference of the different types of filters, because filters can't work across every single frequency band. Lumped element, for example, we are able to operate from down at 1 megahertz all the way up to 22 gigahertz. Ceramics are very narrow, from about 500 megahertz to 6 gigahertz, and then cavity and comb line filters will work from 300 up to 26. And then the bandwidth in which you're operating across changes. So each one is unique in many different ways. And so there are cases where we can't use certain technology because physics won't allow it, or the constraint of size, weight, maybe power handling will extremely change the design to the point where it's just not feasible for the system it's being used in. So we have to work very closely with our customers in order to define what they're looking for, because a lot of times not everyone's an expert in every single portion of the design. And so we want to be able to add that value to them of giving them advice on how to make adjustments and trade-offs that will most benefit them. There's different considerations as well that impact the performance of the layout of the filter. The power handling, the phase linearity and group delay as we talk about radar systems. Those become big factors in phase matching of cables. Well, we might need a phase match filters because they will change the phase of your system. And those are all things that we get into talks to with our customers when we're trying to define what type of filter they need. With that, I'm going to pass it over to Matt O'Leary at XMA.
All right, hi everybody, how you doing? My name is Matt O'Leary. I'm the Director of Sales and Marketing for XMA Corporation, a role I've been in for 2 years. I'm a mechanical engineer, and I've I've been working in the high-performing interconnect industry since 2019. So at XMA, we manufacture attenuators, terminations, power dividers, couplers, equalizers, and DC blocks, among a couple of other products. And at our headquarters, which is actually 45 minutes north of here in Manchester, New Hampshire, we have a thin film lab where we manufacture thin film resistors. And so my presentation is going to be about how we design thin films and how we think about sources of loss, sources of noise, and sources of distortion with that. But because we have our thin film lab at our facility, we're totally vertically integrated. We have total control of our design, of our quality, our design, and our subject matter experts are a big part of that. And so going on to the next slide here. So we're a little bit different than maybe some of the other people on the panel here when we're thinking about loss. So thin film resistors, they are loss and they cause loss in the system. But we're creating a controlled loss, and this loss is called attenuation. As a signal is traveling from where it's generated through the various circuit boards, cables, and connectors and meets our thin film resistor, this resistor network is creating a specific loss, and this specific loss is specified by the system itself. And so attenuation is determined by materials and geometries in the signal path. And so we're thinking about the materials, the thicknesses of the geometry, thickness and geometry, and the attenuator connections in the signal path itself. And so for material-wise, we sputter nichrome resistors. We sputter nichrome resistors because nichrome allows us, well, number one, nichrome is a resistive material, but number two, it allows us to be very specific with the loss that we specify. We're also going to be passivating our resistors, and some of us talked about here, RF is very sensitive. On our resistors, even a fingerprint can change the RF characteristics to it. And so we get to passivate them to ensure that they're protected and that we keep the RF performance that we're looking for. And then last, we're going to plate these resistors with nickel conductors for help with solderability purposes. When it comes to the thickness and geometry, our substrates, which the substrate is the actual metal piece that we're sputtering on top of, the substrates have to be very precise in dimensions, as this is going to affect our RF characteristics and properties. Sputtering more resistive material on those resistors does not equal a higher controlled loss. The loss is controlled by the thickness and geometry of the entire attenuator system. And when it comes to the size of the attenuator chip, it's very related to the frequency. So the higher that the frequency is, the smaller the chip is actually going to be. And so when it comes for the signals in the attenuator connections in the signal path, precise mechanical components, like everybody here, have to be are required. And when I'm talking about precise mechanical components, I'm talking about what connects, when we're talking about a coaxial attenuator, what connects the attenuator to the actual connectors on the outside. So every component in the signal chain has to be very precise. Those connectors on the external side also have to be extremely precise, based on mil standards or even something higher, or more precise, And so, again, a little different here. Attenuators are a source of noise. So noise is a function of temperature and resistance. As attenuators reduce power in a controlled manner, as I talked about in the previous slide, that power reduction that we're taking away is dissipated as heat, and thermal noise, heat, is the noise that we consider when it comes to thin film. Oops. Here. We can reduce heat and noise by using materials that conduct heat well. And so our goal when we're designing our products is to remove as much heat from that resistor as possible. We need to have a very short and direct heat path, and this is called thermalization. Now, when it comes to distortion, we minimize distortion in a system by having constant attenuation over the required frequency band. And so we're doing this by controlling the impedance by controlling impedance and performance that does not change with frequency. So for example, if we're making a 3 dB attenuator with SMA connectors on either side, we need our attenuator to be, to have 3 dB of attenuation across the entire frequency band, meaning at 2 gigahertz it has a 3 dB of attenuation, 17 gigahertz, 18 gigahertz it has 3 dB of attenuation. We spend a lot of time electrically modeling the RF performance, and this includes adjusting the geometry of the resistor network in order to do so. And we care that series and shunt resistances are balanced over the entire frequency range. So using a case study on noise. So one of XMA's largest markets is in quantum computing. And this is kind of a great real-world example of what we're doing and how we reduce noise in a system. And so in quantum computing, you can see the image there. Cryostats are cooled to millikelvin temperatures. You can see all the cabling that are on a cryostat. They're all connected to, hopefully an XMA attenuator on each stage of the cryostat. And so the design of what we're making, so many attenuators in a cryogenic system, and the goal is to in quantum computing, heat is thermal noise, and so our attenuators from each stage are removing heat until you get to the millikelvin temperatures at the bottom. And so when we're designing, it all starts with the resistor, right? And so I said earlier I sputter nichrome resistors. Nichrome is a proven material at millikelvin temperatures, and that's why a lot of customers in this industry use our product. But it's not just the resistor that's important, it's the other materials that are connected to the resistor and the connector body. And so these materials on the connector body have to be, number one, non-magnetic, because there's a lot of sensitive equipment that is in the cryostat that the magnetism would affect negatively. And the materials that are connected to the resistor have to be thermally conductive. And that's why oftentimes our products that we're doing in quantum computing use copper bodies versus, for a test and measurement application, it would probably be just stainless steel. And for the design, we have to have a flat frequency response, which we electrically model like we talked about on the previous slide. The entire component needs to have low reflections. Resistors need to be accurately laser trimmed, and the components and connectors need to be extremely precise to the mil standards or better. And so last, we need to have a short and direct heat path through the resistor network, and this is especially imperative when it comes to quantum computing. And so we have, you see the cabling that gets from an attenuator to usually an adapter that's going through the plate that goes to another cable, and that happens on a couple of stages. And so we have, kind of multiple solutions, but the two solutions that I'm going to be comparing today and using as this case study is we have, a male-female SMA attenuator that would be connected to an adapter through the plate, and then XMA actually invented a product specifically for quantum computing, which we call the bulkhead attenuator, which is combining both those products in one. And so with thinking about the heat path, the SMA attenuator, we're pulling the heat off the attenuator, which goes to the attenuator body, which then goes to the adapter, and then the heat is then dissipated on the plate. With the bulkhead attenuator, it's actually removing one of those components, and the attenuator is actually mounted directly into the plate. And so the thermal path is actually much shorter because the heat is directly onto the plate. We found that comparing the male-female adapter solution with the bulkhead attenuator, the male-female with adapter, the thermal path is 3 times longer and thus takes much longer to thermalize. And while in use, it actually takes a lot longer for the heat to dissipate out of the system as well. And so, that's what XMA is trying to do when it comes to noise in quantum computing. And so it's not just with our attenuators. You can see there's also infrared radiation that goes into the cryostat as well from external. And so we're also making infrared filters as well, and just finding different ways to remove noise heat from the cryostat system.